Hey there, and welcome to this explainer. I'm going to be your tutor today to help you review and completely master the SEOUS Object-Oriented Concepts lecture right before your exam. Whether you're feeling totally lost or you just need a quick refresher, you are absolutely in the right place. So grab your notes, focus up, and let's get you ready to ace this material. Here's our game plan for today's session. We're going to cover why OOP matters, unpacking encapsulation, grasping data abstraction, understanding inheritance, and finally, decoding polymorphism. To keep you on your toes, we'll do some rapid-fire mini-quizzes along the way to really test your retention. All right, let's jump right into Section 1, why OOP matters. So object-oriented programming is, well, it's basically the ultimate fix for messy code. If you check your lecture notes, OOP is an absolute game changer because it handles software complexity. By breaking things down into manageable objects, it makes upgrading systems super easy. Plus, partitioning work across a massive project way simpler. Now, for your exam, you absolutely need to hit these specific buzzwords: simplicity, modularity, modificationality, extensibility, and maintainability. Seriously, memorize those and you're guaranteed full marks when they ask for the advantages of OOP. Moving right along to Section 2, unpacking encapsulation. Okay, in everyday terms, encapsulation is kind of like a protective bubble. Think about the class construct. Data encapsulation is really just bundling data and functions together into one single entity. But here's the crucial part. It creates strict external interfaces. Why? Because it minimizes interdependencies between separately written modules. You're basically hiding all the messy internal wiring and only exposing exactly what the outside world actually needs to interact with. All right, time for a quick knowledge check to see if we're on the same page. True or false? Encapsulation prevents you from re-implementing modules without affecting the client. Think back to that protective bubble concept we just talked about. The answer is false. Actually, it's the exact opposite. Since clients only rely on that strict external interface, you can go in and completely rewrite the internal workings of the module, and the client literally won't even notice. The impact of your changes is totally contained. Awesome job. Let's tackle Section 3, grasping data abstraction. Now, if encapsulation is the protective bubble, abstraction is kind of like the control panel on the outside of it. Simply put, abstraction is all about representing the essential features without getting bogged down in the overwhelming background details or explanations. It's how we extract common features to create a single, clean interface to handle multiple tasks. Take a look at this. It brilliantly shows abstraction in the wild. We've got the class student here, and it contains data members like roll_now and name, plus a member function called read. Now, because everything is bundled up in this single class, it supports encapsulation. But when other classes try to interact with this student class, they aren't allowed to see the complete inner workings. They only see the specific, essential features they have access to. That exact feature, hiding the inner complexity, that's abstraction. Okay, listen up, because you are definitely going to see this list on your test. A good abstraction has 4 very specific properties. 1, meaningful naming. 2, minimum features. 3, complete details. And 4, coherence. Seriously, take a mental screenshot of this right now. If the exam asks you to define a good abstraction, you need to list those exact 4 properties. Let's do another quick memory test before we move forward. Fill in the blank for me. A good abstraction must have a what way of naming that reflects the object's attributes and behaviors. Meaningful. Yeah, meaningful naming. You want your data types to perfectly reflect what they actually do. The name itself should tell another programmer right away what the object's attributes and behaviors are. Okay, you're doing great. Section 4, understanding inheritance. So in the real world, you inherit traits from your parents, right? Well, in OOP, classes do the exact same thing. Inheritance is basically just the process of creating a brand new class from an already existing one. The whole goal here is reusability. I mean, why write the exact same code twice when you can just inherit it? Notice how cleanly this maps out the concept. At the top, the base class has feature A, feature B, and feature C. Below that, the derived class automatically gets those exact same features passed down to it. But it doesn't just copy the base class. It actually extends it by adding its own brand new thing, feature D. It inherits the old stuff and introduces the new stuff. Time for a pop quiz to lock this concept in. What's the formal term your professor uses for the new class that's created during inheritance? It's called the derived class. The original one is your existing or base class, and the new one is the derived class. Make sure you use that specific academic vocabulary on the exam to guarantee full credit. All right, home stretch. Section 5, Decoding Polymorphism. Polymorphism is a big word, but it basically just means different forms of data being handled by the exact same type of process. Really, it's the ability of different objects to respond to the same process or function call, but doing it in their own entirely unique way. The crucial thing to remember here is actually in the Greek roots, which I know your professor explicitly highlights. Poly means many, and morphos means forms, so many forms. This gives our code incredible flexibility because a single function name can take on many different forms depending on the specific data it's interacting with. Here is your final knowledge check for today's study session. Fill in the blank. Polymorphism is achieved by various forms of what, which allows operators and functions to behave differently in different contexts. The answer is overloading. Overloading operators or functions is the primary engine that makes polymorphism work in the real world. It lets the exact same operator behave totally differently depending on the context it's placed in. And there you have it. You've mastered encapsulation, abstraction, inheritance, and polymorphism. You are officially ready to crush this exam. But as you pack up your notes, I want to leave you with one final thought to really test your deep understanding. If you had to sit down today and build a massive, highly complex software system from scratch, which of these 4 features do you think is the absolute most vital to prevent total chaos in your codebase? Think about how they all interlock. Good luck on your test and keep explaining the world around you.